When you see lavas and ashes erupting out of a volcano, you probably don't give much thought to what the lavas are going to look like when they've cooled down. At first sight, these lavas on Mount Etna all look much the same, and indeed they're all basalts. But there are chemical and mineralogical differences between the basalts, making up one lava flow and the next. Those differences can be due to differences in the original magma compositions, but they can also be due to changes which occur as the magma cools and minerals crystallize. And that's what we're going to look at in this program. On the surface, lava cools rapidly, but even while the magma is still deep within the volcano, it's cooling slowly, and crystals can form. This isn't a rock melt crystallizing, it's a pure organic compound. But in principle, it's the same as if we cooled a melt of a single mineral. Only the temperature's different, about 60 degrees centigrade instead of about 1,000 or more. But few rocks are made of just one mineral. This is a basalt from Etna. Those holes are vesicles that are formed by gases escaping as the lava cooled. And there are phenocrysts of black clinopyroxene, of greenish olivine, and white plagioclase feldspar. And the fine-grained ground mass has the same minerals in it. Now, the liquid from which this rock crystallized wasn't simply a mixture of those three minerals. It was a good deal more complicated than that. It was a magma with just the right composition to permit those three minerals to form as it cooled. But all the same, it does turn out that rock melts do behave as if they were mixtures of minerals. But to experiment with rock melts, you need temperatures of more than 1,000 degrees. So we'll start by simulating the behavior of a rock melt by using two organic compounds to represent two minerals. These are two pure organic compounds, A and B. Orange A melts and crystallizes at 67 degrees centigrade. Colorless B melts and crystallizes at 89 degrees centigrade, about 22 degrees centigrade more than A. Now over here are molten mixtures of A and B. This one's got 80% B, only 20% A. Still pretty dark. But B has the higher crystallization temperature of the two. Now, which of the two is going to crystallize first as we cool the mixture? Crystals are forming now. We need to suck off some of the liquid to see what they are. They're colorless. So as you may have predicted, B crystallized first, not A or a mixture of the two. Now the second melt is much richer in A, with only 20% B. What's going to happen this time? The crystals are orange, so it's either pure A or a mixture of A and B. In fact, the crystals are pure A, and that's a very important result. Because B crystallized first from the B-rich mixtures, but A crystallized first from the mixtures rich in A, even though B has the higher crystallization temperature. Well, now let's do a more refined experiment. These circular dishes contain melts ranging in composition from pure A to pure B. Each has got its own temperature indicator. And I'll cool them down so that you can observe the temperature at which the first crystals appear in each dish. As soon as crystals appear in a dish, I'll stop its temperature indicator to record the crystallizing temperature. Well, now to get this to work properly, it has to be done very slowly. So to save time, you'll be seeing an edited version of the whole experiment. The temperature is just 89 degrees centigrade, and something's happening in the dish containing pure B. It's difficult to see, but in the 80% B melt, there are now some crystals, and the temperature is 77 degrees centigrade. Now we're at 67 degrees centigrade. That's the crystallizing temperature of pure A, and it's turning solid. Now at 62 degrees centigrade, 60% B is crystallizing. Now 20% B at 57 degrees centigrade. And finally, at just under 50 degrees centigrade, 40% B. So each melt starts to crystallize at a different temperature. And the lowest temperature was for 40% B. Now, if we did a few more experiments, we could get a curve that looks like this. The minimum temperature of crystallization of mixtures of A and B is about 46 degrees centigrade, and the compositions 43% B and 57% A. This point is called the eutectic. For compositions to the right of the eutectic, mixtures with more than 43% B, crystals of pure B will separate from the melt. And to the left of the eutectic, pure A will crystallize first. But what happens when we heat the solids up again? Which one will begin to melt first? Well, let's try it and see. Well, we're at 46 degrees centigrade. That's the temperature of the eutectic. And there's some liquid in the 40% B dish. In fact, there's some liquid in all the dishes that have got mixtures of A and B. At this temperature, only the pure A and B samples are still completely solid. So all the mixtures begin to melt at the eutectic temperature. Well, I think that's all pretty surprising, and it certainly isn't easy to predict. But we've now got a way of describing what happens in systems like this. This is a phase diagram, and it's by the study and use of phase diagrams that we can begin to understand more about what happens when rock melts cool. Well, phase diagrams are really little more than a special kind of graph. We've got temperature plotted up here, and composition along the bottom from pure A to pure B. And this phase diagram is for a particular pressure, atmospheric pressure. If we change the pressure, the shape of the diagram would change, but the principles would stay the same. These are the three important features. The liquidus defines the crystallization temperatures for molten mixtures of all proportions of A and B. The eutectic point represents the composition which crystallizes and melts at the lowest temperature. And notice that the solidus goes up each side to represent the melting of pure A and pure B. The horizontal part of the solidus tells us that all mixtures of A and B start to melt at the eutectic temperature. So below the solidus, all mixtures are solid, and above the liquidus, all mixtures are liquid. Well, the best way to understand phase diagrams is to use them. So let's see what happens when a melt of a particular composition cools. This composition. Now, the first thing to realize is that if the melt has that composition, then the final solid has to have the same composition as well, provided nothing's been taken out or put into the system in the meantime. Now, at first, when we cool the melt, nothing happens, but eventually it will reach the liquidus. At that point, crystals of pure B will begin to separate. That will make the liquid depleted in B, and so as the temperature falls further, crystals of B separate, and the composition of the liquid changes down temperature along the liquidus until it arrives at the eutectic. Now, only at this point can A begin to crystallize from the melt. The liquid can't cool anymore or change its composition. So what's going to happen? Both A and B will crystallize together in the proportions of the eutectic composition and at the eutectic temperature until all the melt is solidified, and only then can the temperature begin to fall again. So this eutectic point is the only place in the system where A and B can crystallize together. But remember that this is the bulk composition of the solid. And we reach that by first crystallizing pure B as the liquid moves down the eutectic, and then by crystallizing A and B together in the proportions of the eutectic at the eutectic temperature. Now exactly the same thing happens for mixtures that are rich in A, except of course this time pure A will separate first. So for any mixture in this sort of system, the last liquid to crystallize will always have the eutectic composition, and it will always crystallize at the eutectic temperature. But the composition of the solid you end up with has to be the same as the liquid you started with, provided nothing's been removed from the system or added to it. And of course, that composition has to be the same for the whole sample, whatever the temperature. So, at this temperature, for instance, the composition of the whole sample is there, but it's made up of two phases: crystals of pure B and the liquid of this composition on the liquidus. Well, now that's the sort of behavior you might expect to find in some rocks consisting of only two minerals. But most rocks consist of more than two minerals. So how do we study the crystallization of melts with three components in them, say A, B, and C? These are the liquidus curves for each pair of three components: AB, BC, and CA. And we can combine them quite simply like this to bring the B and the C ends together. It leaves only the A ends. To do that, we need to move into three dimensions. And this triangular system links the liquidus curves for our three components. And of course, height represents temperature. And mixtures of A and B and C will plot inside this volume. And of course, there'll be some sort of three-dimensional liquidus surface linking these two-dimensional liquidus curves along the sides. And we can determine the shape of that liquidus surface by experiment. But first we've got to know how to plot mixtures of A and B and C in here. Now this is a two-dimensional plan view of our three-component system. The sides represent the two-component system, so that you've got 100% A here, 100% B, and C. The side opposite the A corner has, of course, 0% A. And compositions along any particular line parallel to this side will have the same percentage of A. And we can build up a grid of compositions for A in that way. And we can do the same for B and for C. So this point has a composition of 30% A and 50% B, 20% C. The numbers have got to add up to 100, of course. And now that we can plot compositions of our three components inside the model, we can go ahead. By cooling melts of different proportions of A and B and C, we can find out the temperatures when they begin to crystallize. And of course, we can plot those temperatures vertically on the model. If we do that for many different compositions, we'll eventually define the liquidus surface. And the main features of that liquidus surface are these three valleys. The bottoms of the valleys are called cotectics, and the lowest temperature point is the ternary eutectic. If I now cool a melt that's rich in, say, C, when it intersects the liquidus, crystallization of pure C is going to drive the melt away from the C corner down to the cotectic. When it reaches the cotectic, the only way the liquid can move is down the cotectic valley. It changes direction away then from both the C and the A corners, which means that pure A must be crystallizing as well as pure C. In other words, a cotectic in a ternary system is the same as a eutectic in a binary system. When a liquid reaches it, a second phase has to crystallize. Anyway, our melt goes on down the cotectic, crystallizing C and A as it goes, until it reaches the ternary eutectic. And there, something else has got to happen. Crystals of B have got to come out. And so the melt's going to stay there in the ternary eutectic at the composition and temperature of the eutectic, crystallizing A, B, and C in fixed proportions until all the melt's gone. But of course, the final solid product has to have the composition of the melt you started with. And that's made up of crystals of C, which started crystallizing as the melt moved down the liquidus, along with crystals of A that came out with C as the liquid moved down to the cotectic, and of crystals of A and C, B and C and A as the liquid finished crystallizing at the ternary eutectic. Well, three-dimensional models are great fun to work with, but they're a bit cumbersome. It's much easier to use two-dimensional diagrams. And as temperature is represented vertically on these models, then points of equal height will be points of equal temperature. And if we join points of equal temperature on such a surface, we can get temperature contours. And we can use those contours to depict the surface of the three-component system, liquidus, in two dimensions, just as you use height contours on a map. The contours decrease down the slopes from the corners to the cotectic valleys, the dark lines. And the cotectics meet at the lowest point, the ternary eutectic. But rather than use this phase diagram to follow the crystallization of a melt, I'll use this one because it can be applied to igneous rocks. Now this is the phase diagram for diopside, which is a pyroxene, an albite and an orthite, which are end members of the plagioclase series. It's similar in principle to what you've seen before, except that there's no ternary eutectic, and instead there's this long cotectic almost bisecting the diagram. Now let's see what happens when a melt of this composition cools. It's about 60% diopside, 25% anorthite, and about 15% albite. When it cools, it'll intersect the liquidus surface at 1300 degrees centigrade. And crystals of diopside will begin to separate. That will drive the melt away from the diopside corner down to the cotectic. At that point, a second phase has to crystallize, and the liquid has to move down the cotectic in that direction. That can only happen if anorthite is removed as well as diopside. But it won't be pure anorthite that crystallizes. We know it won't be pure anorthite because we know that the plagioclase feldspars are a solid solution series. And to see how that affects crystallization in this system, we need to look at the two-component system for albite and anorthite. Well, it's different. The liquidus curves all the way down from the anorthite end to the albite end. The solidus is curved too, and there's no eutectic. But the basic principles haven't changed. So let's see what happens when we cool a melt that's got 60% anorthite, 40% albite. There's the composition of the liquid, and that's got to also be the composition of the final solid. As the melt cools, it'll intersect the liquidus there, and as before, the composition of the solid at that temperature must plot here on the solidus. Now that's not pure anorthite. It's about 90% anorthite. That is something new. Well, now, as anorthite-rich crystals separate from the melt, the composition of the liquid must move on down the liquidus. When it reaches, say, this temperature, the composition of the solid has to be there. And that means that the composition of the solid has had to change from there to there in that temperature interval. Now, the only way for that to happen is for the cooling to be slow enough for equilibrium to be maintained between the solid and the liquid. There's got to be continuous reaction, continuous diffusion of ions between crystal and liquid, so that as the liquid cools and changes composition along here, the composition of the solid changes along here. And at any particular temperature, the liquid is always richer in albite than are the crystals. And as cooling proceeds, of course, both liquid and solid get richer in the albite component. But that's got to stop somewhere. And it's fairly clear where it's got to stop. It's got to stop where the composition of the solid reaches the composition of the melt you started with. And at that temperature, the last few drops of liquid remaining plot there on the liquidus, very rich in albite. And your final solid will be made up of homogeneous crystals, solid solutions that consist of 60% anorthite, 40% albite, but only if cooling has been slow enough for equilibrium to be maintained. Well, now let's go back to our three-component system and see where we've got to. Well, we've got our melt, cooling and crystallizing diopside and moving on down to the cotectic at this point. Now, we know the composition of the temperature of the melt at that point. And so we can use what we know about the two-component plagioclase system to work out the composition of the plagioclase feldspar on the solidus that's crystallizing from this melt. And we can also work out how the composition of the plagioclase crystals will change along the solidus as the composition of the melt changes down the cotectic with falling temperature. That's really a geometrical exercise, and you'll find out more about it elsewhere in the course. But what I want to do now is to show you that we can begin to gain some insight into what happens when rock melts cool. Now, here's a thin section of a basalt from Etna. There's a big phenocryst of clinopyroxene not far from diopside in composition, and it's set in a fine-grained ground mass of plagioclase and pyroxene. Pyroxene was obviously the first mineral phase to crystallize as this basalt cooled. So applying what we know of this three-component system, we can conclude that the composition of the rock melt lay on this side of the cotectic, so that pyroxene crystallized first. Now look at this thin section of another basalt, also from Etna. Those are plagioclase phenocrysts in a fine-grained ground mass of pyroxene and plagioclase. So in this one, plagioclase was the first mineral phase to crystallize. And it's easy to see roughly where composition of this rock melt might fall on our three-component system. It must have been on this side of the cotectic, so that plagioclase crystallized first. And we can say something else about this rock. There are big crystals of plagioclase forming the phenocrysts and little crystals of plagioclase in the ground mass. Now, those small crystals must have formed after the big ones, as the lava was quickly cooled after it erupted. And they're richer in albite than the big crystals. We can work out why that is. The big crystals that formed first were richer in anorthite than the melt, and so the melt was correspondingly richer in albite. So that when the lava erupted, that melt solidified to form the small albite-rich plagioclase feldspar crystals in the ground mass. And quite clearly, equilibrium between crystals and liquid wasn't maintained when that basalt formed. And because rock melts crystallize over a range of temperatures and pressures, it's quite common for equilibrium not to be maintained. What's more, systems don't remain closed. There's plenty of scope for early formed crystals to sink out of magmas or float to the top. And when they do, they change the composition of the remaining magma. And that's where we begin to get into the topic of crystal fractionation, which we'll be looking at in the next program.